explainer variable, outcome variable. Okay, let me see how I can mute this. Okay, so these that is essentially in a nutshell what regression is. I'm sure you must have gone through some of the finer details of what a regression is. Sorry, keep interrupting there. So there are assumptions, just like any other form of statistical inference and hypothesis testing. There are assumptions for linear regression, and from the word linear, it should be obvious that, okay, you are assuming these two variables you are testing have a linear relationship. So that is one of the assumptions. The other assumption is that at least one of the variables needs to be normally distributed. And then there is also something called homoscedasticity, which you must have heard of again in the general class, which means that the residuals, basically the, let me see if I can find your class notes. Okay, to take a bit too much time. So anyways, so there's homoscedasticity, there's linearity, there is normal distribution, and I think there's another assumption. If anyone remembers, you can type it in the chat box. So we're going to start now, assuming that everyone knows what linear regression is. We're going to be using SPSS. We're using the residentdoctors.csv dataset. So I'm just going to go into my datasets folder. Okay, yep, resident doctors, okay. Okay, we have the data sets imported. So whenever I import data sets, I like to look at the variable view. It helps me to determine the number of variables in the data set. Looking at the data view, also just scrolling through, will help me quickly explore what it looks like in terms of the number of observations. So here, when you look this way, you see the types of variables. So going back to the questions, the question here is that we should determine if hours worked is related to mental health score. So can anyone volunteer to tell us which one is the outcome variable and which one is the predictor variable? Does anyone have a guess? Okay, so yeah, someone is unmuted. Go ahead, Taiwo.
Okay, I think hours worked is the explanatory variable, and mental health score is the outcome.
Okay, that's great. What other name would you call the explanatory variable?
Independent variable.
independent variable, also
Predictor variable.
predictor variable. Okay. And this is the outcome variable or the dependent variable. Okay, so we want to know if this can predict this. So we have imported the data set. Usually these things is just point and click. You can see it's just 3 steps. So we go into SPSS. Do we have a variable called mental health score? Sorry. Yes, we do. Do we have a variable called hours worked? Yes, we do. So we want to know if this can predict this. We go to analyze, and then we go to regression, and then we go to linear regression. So the dialog box is the same for what's it called, for both simple and multiple. In this case, we are doing simple because we have only one predictor variable. So what is the dependent or outcome variable? Is the mental health score. We put it in here. What's the independent variable? Is the hours worked, and then we put that in. Now, this method, we're going to leave it here. When we come to, we're going to just leave it as it is. It doesn't really matter for simple linear regression. It becomes a bit more usable when you talk about the multiple regression. So as usual, you have other options that you can tweak, things like the statistics, things like whether you want it to come out with some kind of plots or a histogram or a normal probability plot. So for example, the normal probability plot will help you know whether these variables are normally distributed. So let's just go ahead and click that. Then the statistics, you want to know whether it should give you some additional statistics depending on what you are trying to do. As usual, we're trying to keep things simple. So we are leaving everything here. Maybe just check the confidence intervals. And then we click on OK. Okay, so this is the output. It tells you that what you did is a regression. It tells you the variables that you entered / removed. Again, this I will explain when we come to multiple regression. And then it tells you the model summary. So the model summary tells you what this R is the correlation coefficient, which is which tells you how linear the relationship is between the hours worked and the mental health score, which are both, what are they? Continuous variables. So a correlation coefficient of, let's say, 0.2 and less is considered to be very weak, or maybe there's no correlation. There is mildly correlated if it's between 0.2 and 0.4, moderate between 0.4 and 0.6. 0.6 to 0.8 is strong, and anything greater than 0.8 is very strong. So the correlation coefficient itself has a value between 0 and 1, or rather you'd say a value between -1 and +1. So it can be either negative or positive. If it's positive, it means that the as one variable increases, the other increases. But if it is negative, it means that while one variable increases, the other decreases. So I hope that the point about the correlation is clear. So the R square is basically this R squared, but it also tells a story of how fitting the model is. So this whole model, if you look at the regression we've just done, it aims to predict the mental health score from the number of hours worked by the resident doctors. So the whole model, how much does it fit? How well does it predict? How well does the independent variable predict the dependent variable is what the R-square answers. So this is a decimal, but it can be expressed in form of percentage when you move 2 decimal points. So this is basically just 4.2% of the overall variability of the mental health score can be predicted using this model, which means it's not a very good model. So we have not looked at anything like p-values or anything like that. Then this adjusted R-square is basically the SPSS running some forms of statistical corrections on the R-square itself. So ANOVA is basically like the ANOVA that you've done before, and it's giving you some outputs. So all the interpretations that you know for ANOVA remain the same, like the F statistic, which tells you whether or not there is a whether or not the assumption of homoscedasticity has been satisfied. So this table that says coefficients is the actual regression. Now, when you do a regression, you are trying to come up with a formula that, sorry, let me see. Sorry, not notes. Maybe, yeah, maybe notes. So you are trying to come up with a formula that comes in the form of y equals a plus bx or something like that, where this is your dependent and this is your independent. So in this case, our independent variable is mental health score. I'm just going to type it like this, and then equals A. Now we're putting in A here, but if you look here, this A represents a constant. If you look at this table, you see that the constant is 26.35 or 26.4. So I'm going to remove this this A, and I'm going to write 26.4. Then plus, is it plus or minus? How do you know if you are going to add a plus or minus here? You look at the sign on the coefficient. So the coefficient for hours worked is minus 0.037 or minus 0.04. So I'm going to remove this plus and put a minus and say 0.04. Then multiplied by hours worked. So that is our linear regression. So if we look further at the table here, we can see that for the coefficients themselves, some standard error has been calculated. So you can use this to calculate a standard deviation for this if you like. Then the standardized coefficient beta. Now this is this tells you how much of the whole model depends on this variable. If you remember what we said about R square, we said R square tells you overall how accurate is this model, and the model accuracy is this 4.2%. But in the standardized coefficient beta, it tells you how accurate is this particular variable in predicting the outcome variable. And this is minus 2 points. Of course, you would not use a minus, but it's 20% of the whole model. It accounts for 20% of the whole model. So what all of this is telling you is that you need to look for other reasons for whatever the value of the mental health score that you are seeing. So if you are seeing that the participants from your study have a high mental health score, high meaning that the higher the number, meaning that the worse the mental health score. So for all of that, you need to look for a better reason to explain it, not just the number of hours they work. Jerry, your hand is up.
Yes, I'm sorry, I'm a little I'll need you to guide me on this. So first of all, from the regression equation that you worked out, if you just go over it again, I know that the y is what we want to predict. So that y becomes the mental health score. And then you said A. So I'm relating this to the normal equation of line, y equals to mx plus c. Using all these letters are very confusing. So y equals to mx plus c. C would be the intercept on y when x is equals to 0. Right? And that would be A in this case. That would be A in your own case.
Yep.
Then B would be the slope of the line, which is the increase or decrease factor. That's the slope, which is how much x.
So let's do it.
Mx plus c.
Right.
Yes,
so this x is your predictor variable.
Yes.
Y here is mental health score. That has not changed.
Yes.
X is the number of hours worked. So
Yes.
it's just a question of arrangement. So
Okay.
X is the number of hours worked, which is your independent variable. C is your intercept or constant. So
Yes, constant.
So when you bring where is it now? When you bring your y is mental health score, and then you say mx, so x is the hours worked. Your m, which is the coefficient of
constant.
No, your m here is the coefficient of x, the coefficient of your predictor variable.
Yes.
So you come here, your predictor variable is hours worked. So you come under B. B is your coefficient. So you come here. What is the number here? Is 0.037, which I rounded to 0.04. Then that is the reason why, but it's a negative, it carries a negative value. And that's why I picked it like this and pasted it. And then where is it? Your constant is 26.352, which is 26.4. So it's just a rearrangement, basically.
So the value in front of x is actually the coefficient.
Yes.
As a coefficient. Okay, then secondly, I think I get that now. Secondly, I'm a little confused from the R square to the standardized coefficient beta. I was under the impression before that the R square is actually the coefficient of determination, and it tells the proportion of the independent variable that is accounting for the changes we see, or for the regression equation. So the higher it is in proportion, it means that our predictor variable is actually predicting more of the outcome we see. But I'm a little confused.
That is correct if you are doing a simple regression, which is what we are doing here. But if you are doing a multiple regression, which we are going to get into, I want to go in further to see how good a particular variable is at predicting the outcome. Then the standardized coefficients become important, and you also begin to consider that number because it gives you more specificity to what contribution that particular variable makes to the model.
Yeah.
Does
I've
that make
seen
sense?
the light. I've seen the light.
Yeah. Any other questions? So let's go back to the question that we were asked. So they said we should select this as dependent, we should select this as independent. We have done that. And they asked us how we interpret our findings. Well, we have kind of interpreted our findings to say that you can you can predict the mental health score by adding 26.4 to whatever you get from this result. So you multiply the number of hours the resident works with 0.04 negative and subtract from this. Does that make sense? So if we say this number of hours worked per week, by the way, so let's just put it to the test. Let's say there's this hypothetical resident. Most of you here are health professionals. So let's say there's this hypothetical resident that has so much energy that it works 90 hours per week or even 120 hours per week. So what we're going to put here is 120. So Jerry, can you multiply 120 here?
Okay, so unfortunately, I just got back network and I was hearing Jerry. So
okay, no worries. I was just
yes.
We are doing a hypothetical. We are testing this model to see to calculate the mental health score of a hypothetical resident that works 120 hours per week. So what we do is we have this constant and then we multiply this negative 0.04 by the number of hours per week and subtract it from that. So does anyone have a calculator? Let me see calculator. So if anyone has done it, you can let us know. So we do 0.04 multiplied by 120, which is 4.8. So you subtract 4.8 from 26.4 is 21.6. So for that, for this resident Q is mental health score would be 21.6. So what did we do here? We have taken a sample of resident doctors. Let's check the data set. There are about 161 resident doctors. 161, or is there a header? Yeah, 161 resident doctors in this data set. But we are assuming that not each and every resident doctor in the hospital where this study took place was sampled. Only those who consented or were available. Now we came up with this question. Okay, what if hypothetically there's someone who works 120 hours per week? Can we predict what their mental health score would be based on this data? So that is what this is giving us. But then, can we trust this as 100%? 100%? No. Why? Because of the interpretation of the R square here, which is 4.2%. So only 4.2% of the mental, sorry, of the mental health score can be predicted from this model. So, but the purpose of this class is not only to demonstrate relationships that work, it's also to demonstrate how we go about determining if there's a relationship in the first place. So that's the whole idea. Are we happy with simple linear regression, or do we have any questions? Okay. So let's go to the next example. Okay, so these are the same outputs that we had from our SPSS, and we have discussed them at length.
Sorry.
Yeah.
I just have one question. What about the F statistics and significance?
Yes.
Significance.
So
how do they play in this regard in the ANOVA table?
Yes. So like I said, the F statistic is checking for the homoscedasticity, just like you are checking in the t-test and ANOVA. So I can't remember what the what's it called? The null hypothesis. The null hypothesis for this would be that the variances are equal. So there's no difference between the variances. And if you see here that the significance is much less than 0.05, it means that it has actually failed that Levin's test. So the whole idea of going now to interpret this model summary and also interpreting the coefficients and all that is an academic exercise because it has failed this Levin's test. Does that make sense? If you remember from our class in the when we did t-test, we said we want the p-value for Levin's test to be non-significant.
Yes,
okay.
I'm just a little confused as to what we heard yesterday.
Okay. What you heard yesterday, okay, what did you hear?
So it's that we want it to be significant. So it means that there is no variance. So the null hypothesis would state that there is no relationship between the variables, like they are not collinear.
Okay.
So there's no collinearity or something. So it means that we want it actually to be significant for us to reject the null and accept the whole the alternative hypothesis that indeed there is collinearity.
Okay.
And then we can now proceed. I don't know if that is the same thing or I'm confused.
Okay, so give me a second. Let's clear that up before we move. Okay, where am I? Let's come back. Okay, so the F statistic on the ANOVA table for the regression explains that it basically explains that it has a null hypothesis to say that the variables are not related, like you have stated. So I think I misinterpreted that to be the F statistic from the Levin's test. So thanks for drawing my attention to that. So the example that we have done, that we have just demonstrated, shows you how to do a linear regression, a simple linear regression using two continuous variables, which means that the predictor is continuous and the outcome is also continuous. However, you can also do that. You can also do a linear regression with a binary predictor. And in this case, we are trying to see if the number of hours that have been worked by the residents, we are now turning it into a categorical variable to see if a hypothetical benchmark of 70 hours a week is the limit, above which, meaning that anybody that works more than 70 hours might end up having a worse mental health score. So we are recoding the mental health score and the number of hours worked into a binary variable. So we go to...
Sorry, can't see your screen if you are sharing.
Oh, okay. Thanks for bringing my attention. Can anyone see my screen? It shows that I'm sharing.
Yes.
So let me present again. So now can you see? You should be able to see my screen. Okay, so this is what I was explaining when we say using a binary predictor to predict to conduct a linear regression. In the previous example, we had used the number of hours worked, just raw numbers, to predict the mental health score. So now what if someone somewhere says no, or maybe a study elsewhere shows that actually when residents work more than, let's say, 70 hours in a week is when they begin to show mental health, that's when they have to begin to have mental health problems. Then we can come here and record our number of hours worked in a way that it sets a cutoff of people who have worked more than 70 hours and people who have worked less than 70 hours. And that's what we're trying to do here. So before we even go ahead to run the regression, we're going to transform this variable, hours worked, into another variable called hours GT70. Does that make sense?
Yes, but just at the top of my head, that 70, is it just hypothetical or you can deduce it from the model?
It's just hypothetical. So looking at this, I would say maybe you are doing your study, you have done your study and you are in the process of analyzing. You have not found any direct relationship between the number of hours worked and the mental health score. However, let's say you did your study in Lagos, but another study in Accra says that, oh, actually the benchmark is 70 hours. what they found is that anyone who has worked doctors who have worked more than 70 hours in 1 week have come out with poorer mental health scores. Then you can recode your hours work variable to set a cutoff of 70 and enter that into the model. So it will now be checking those who are who have worked above 70 hours and those who have worked less than 70 hours or 70 hours and less in a week, and trying to use that to predict the outcome of mental health score. So let me demonstrate how we recode this into a categorical variable, and we can do the regression model and see if it changes anything. So this is the variable we want to change. So we go to analyze. There should be an option here that says transform, or rather transform itself here, transform, and then recode into different variables. The reason why we're selecting this is because we want it to create a new variable at the end of the transformation. Otherwise, what's going to happen is that this hours worked variable will end up getting affected by whatever change we're making. We'll code into different variables. So this is the input variable, mental health score. The output variable is, what's it called? Hours GT70, I think, hours GT70. Hours GT70. And then we click on change. We say old and new values. So we use range lowest through value. So this here, what we are telling SPSS is that the lowest value within your data set, whether that is 1, 2, 3, 4, whatever the value is, up to 70. So everything from 0 to 70 would be recorded into a value here. So let's see what are we asked to do. So we put that as 1. So sorry, I've done it. If I go ahead this way, we are going to get the same answer, but it's going to be flipped. So rather, we are taking everything that is 70 and above. If you do this, you are doing 70 and below. But if you do this, you are doing 70 and above, which is what we want to know. So if we say 70 here, and then we code it, the variable, remember it has a binary, the variable is a binary variable, so we are giving it values of 1. So anything that is 70 or above is given a value of 1 by SPSS from this hours worked variable. And then all other values, someone's mic is unmuted.
Yeah, sorry, I wanted to ask, it says hours greater than 70, so do we include 70?
Yes, just for simplicity, but if we want to be very strict, we would make it, I don't know, 70.0001 or something like that. Sorry, what happened? Did I not save my 70? Give it a value of 1. Yeah, it's here. And then all other values, give it a value of 0. And you add that as well. Yep. So if 70 or above, code it as 1, or else you code it as 0. Then you continue. So that's already given the output variable, the name hours GT70, and then you click OK. So it gives you this. This is what it has done. It has done the recoding. And if you look here in the list of variables, where we previously had 10 variables, we now have 11 variables. And then we can reduce the number of decimals because it's just 0 and 1. If you come to the data view and you look at hours GT70, you look at hours worked. Has it worked? This hasn't worked. So it's supposed to give us, for example, here where we have hours worked 80, it's supposed to give us 1, 70, 90, anything 70 and above. So let's go back in and check why it's not doing that. Someone, so who raised their hands first? Gideon, yeah.
So I don't know. So I don't know. I wanted to ask if we are using a visual binding. Will
Sorry?
it give us this? I mean, visual binding. There's another. This another the transformation. The transform this in visual binding.
Visual binding.
Yes. Will it give us the same thing that we are looking for?
So I'm not quite sure what this does, but
So,
it's.
So because
how have you used it in the past?
Okay, so Jerry was more particular about higher than 70. So visual binding, I feel can do that better. So
Okay.
if you click visual binding, so you bring the
score.
yes into it. You click it.
So just click continue.
Yes, click yes continue. So you first of all put the variable name. No, these are the binding variable. No, come to binding variable first. A bind variable.
Yeah, that's the new variable, right?
Yes, the new variable.
Okay.
Okay, so since we are looking for above 70, we come to where we have 1 under value, which is the highest. So we can impute 70 there. Okay. Okay, so we want okay, so we are looking at above 70. Okay, so if we are looking at above 70, we can above 70 highest. So we can exclude 70.
So here we exclude 70.
Yes, we exclude 70. Then the label name will now be 1. Then so for this one now, okay, fine. Sorry, let's go back to the first one. So since we are looking at 70, put 70, put in, so we click include 70, sorry. 70.
Include 70.
Yes, include 70. So here we label 0. Since we are looking at 0,
that will be 70 and less.
Yes. So here now, the highest value here is, I can't really see the screen very well. The highest value on the red, where we have this red.
Yep, that's where it is.
Yes, I don't know the highest there. It should have given us highest and lowest.
Yeah, it's not really showing that much. I think there's 73 or something. Yeah.
Okay, so that should be our highest. Where we put there. In the second one for the second group, yes.
Okay, 73 here, but that's not the highest value in the variable.
So that means that I don't know. It's possible it's not the variable you are picking for this, but it should bring.
Yeah. Yes, I think I realize what has happened now. Let me go back to. So let me just go back to this this hours GT and clear this variable. So we are trying to
Can I just ask a
transform.
question before you go?
Yes.
Yes, I was just wondering why we selected mental health score as the variable.
Okay.
If we are
I think that's what
transforming
happened. Yeah. So I selected mental health score, not the hours
not
worked.
hours worked.
Okay. Okay, and then everything else we do it the same. We give this a value. Okay, it's already here. Give it a value of 1 and then else. So let me just remove this so there is no interference. So range 70 through highest, we give it a value of 1, and then all other values we give it 0, and then we continue, and we click change to actually create the new variable, and then we click OK. So we have now created the new variable hours GT70 using hours worked. So when you come back to the data view, that should solve the issue. Yeah. So for any variable, any value that is 70 and above, you'd see a value of 1. 50 is less than 70, you see a value of 0. So your interpretation would be that 70 or more hours a week, not greater than 70 hours a week. So the method that Victor mentioned is not familiar to me, but you can, in your own time, maybe look through and see what visual binning does. Because usually for a lot of these things, you can take them through different approaches. And that's the same with R as well. There are various packages that do the same thing. So I don't want to see these decimal points, so I'll just come here and remove this. And then for the values, the value of 1 means 70 or more hours worked. And the value of 0 means less than 70 hours worked. I'm doing this because I don't want to see 0 and 1 in my output table once I run my regression. So we have recorded the data, the variable, into this hours GT70. Has everyone been able to do this? Have you been able to get to this step?
Sorry, I just have one question. How can't we make it so that those decimals would see actual 0 and 1 instead of 1.00 and 0.00? Because I'm thinking if we remove decimals, if we remove the decimal places, those zeros become missing.
Which zeros?
These
ones, this 1 and 0.
Okay, they are fine now.
Yeah. When you come to the variable view, these decimals, if you want to see 10 decimal places, you can adjust it. So you just adjust, and that was the first thing I did. Adjusted it down to, because it's a binary variable, it doesn't take decimal places. So it will just be confusing. Okay, so let's go to our regression. We go to linear. So here, instead of hours worked, our dependent variable remains the same, but instead of hours worked, our independent variable becomes hours GT 70. Okay, and then we leave all other things constant and we click OK. So we come to our coefficients table, which is our area of interest, and then we can look at this hours GT 70. So based on this table, it says that for every unit increase in the, or rather, for doctors who have worked 70 hours or more, then compared to doctors who have worked less than 70 hours in a week, there is a difference in mental health score by this factor. However, when you go to the right, you'd see that the p-value is non-significant, which means that actually working 70 hours or more does not really is not a good predictor of whether or not the person is going to have a bad mental health score. Yes, Jerry?
So coming back to what we discussed, if you look at the ANOVA, I'm seeing the ANOVA is 0.220.
Yes.
So this will be us doing an academic, what did you call it? Exercise, yeah? Because if you have this and you are seeing that by this, we fail to reject the null hypothesis, saying that the variances is equal, or there is no relationship, it means even running the regression in the first place is just an academic exercise, correct?
Yes. Okay, are there any other questions? Are we getting it, or are we just looking at the screen? Okay, let's look at the class notes. So this is what we did. We used mental health score as the dependent. We used hours GT70 as the independent. And then we came up with a table which gave us these results. So given that our, what's it called? Our significance is 0.220, then we would not use this as a reliable way of predicting. However, if you wanted to just do it for the sake of argument, you would come, where is this? So you would come here. Let's do what we did for the simple one, simple regression. So for people who have worked, if you are comparing people who have worked 70, less than 70 hours to people who are working, who have worked more than 70 hours, using this coefficient, you would basically take the constant. So this is for people who have worked less than 70 hours, and this is for people who have worked more than 70 hours or more. So that would be 26 point, where is it? 24.15. Then this is the coefficient multiplying the number of hours worked. Let's say 90 hours minus 0.6 69 into 90. So yeah, so that gives you the number of that gives you the mental health score for the people who have worked more than 70 hours. Okay, if you want to check for linear trend, so basically, if you want to check, maybe you have done your simple linear regression and it has not really given you any form of relationship, but you think that through these range of values, there may be a particular range where there is some kind of relationship between the number of hours worked and the linear and the mental health score, then you can do another transformation where you split the number of hours worked into several categories. And then for each of these categories, you see which one of them actually, affects the mental health score. So this is just a friendly reminder to remove leftover inputs from an old analysis, just like I did when I wanted to recode the variable into hours GT70. So the name of our new variables would now be hours cat, that's hours categorized. And then we're going to be using these ranges to categorize our independent variable. So let's go here to SPSS. I want to see the data view. Can you see this with the split screen, or should I enlarge everything? Okay, I can see thumbs up. So we are recoding this waste number of hours worked into hours cat using these class bands. So transform, recode into different variables. We're using the hours worked. Where is it? So we delete this. We remove this first, and then we put the hours worked into the box. The new variable name is hours cat. Then we're going to hold our new values. So these we're going to remove. And then we will select the ranges. So from the lowest value in the data set up to 40, it will have a value of 1. And then 40.001 to 60 will have a value of 2, and so on and so forth. So lowest through 40. So 40 and below have a value of 1. Then 40.001 to 60. So we're going to use this range selector. To 60, we'll have a value of 2. 60.001 to 80 has a value of 3. and then 80 and above, so 80 through highest, has a value of 4. So we add this, and then we click continue. Then we click change, and that tells SPSS that we're now ready to create this variable, and then we click OK. So it has recorded the variable. So this is a way to look and just check if what you have done is what you intended to do. For example, the mistake we made in the earlier recoding, where we recorded mental health score instead of hours worked, is here. So if we had just given a bit more of attention to this, we would have known that we used the wrong variable. So that has been done, and then we're now going to use the new variable into the hours. We're going to use this new variable to see how the mental health score changes as you move between level 1, 2, 3, 4, level 1, 2, 3, and 4. So we go to analyze, regression, linear. Our dependent variable is still the mental health score. So remove this. And our new variable of interest now is hours cat. And then we put this in and we say, OK. So it gives us the table. If you look at the, so if you look at the coefficients table, you'll see that the hours category has a coefficient of minus 0.731, and then it is significant. So basically, it's telling us that as you move from one class to the other, from 1 to 2, from 2 to 3, from 3 to 4, the mental health score changes by a factor of 0.731, and this is statistically significant. The model itself has an R square of 0.042, which means the ability of this model to predict the mental health score for this population is about 4.2%. I'm looking at the screen to see if there are any hands raised. Should I call random names? Jerry, Mukhtar, that's funny. Everyone getting it so far? Aziza?
Yeah, we're following. The results here are slightly different.
Results where? On your screen? On your
No, on the one you just did for the categorical, for when you categorized. They are slightly different. It's now showing significance, and it's the same data set. So I don't know whether it is because we use the range that is giving us a range, since there's a lot of variance with the independent data.
No, so it's telling you that the change between the mental health, the change in the mental health score as you step from one category to the other is statistically significant.
Okay.
Does that make sense?
Yeah.
You don't sound convinced.
So I'm just, my head is a cocktail of ideas now, of a lot of things I'm thinking about. Since this is a categorical variable, I remember in one of our classes they said for categorical variables, the best regression to do is logistics variable or something like that. And I am not seeing anything for each of those categories. I
Yeah.
don't know where that comes to play.
Okay.
Like I'm not seeing the categories like 0 to 40, but in which statistics will we see that? Is it?
It's all hidden inside here. It's very weird and not intuitive, just like you have said. So the reason why we are not using logistic, by the way, you use logistics regression when you have a binary outcome. So when the outcome is binary, not when you have categorical explainer variables.
Oh, okay. So if our dependent variable is binary,
yes, then it would be a logistic regression.
Hallelujah.
Okay. So does that make sense now that we are the interpretation also that we each time you change from one, we move from one category to the other, then the mental health score would change by this amount. Does that make sense now? Okay. I'll take silence as yes. Yes, Motslohi. Am I saying your name correctly?
Yes, Motlohi.
Motslohi, okay.
I'm just wondering if the change shows direction in the sense that it shows when we move from maybe a lower category, the score increases or decreases in terms of whether it increases or decreases. Yeah, I'm just wondering whether the information from the results shows that.
Okay. From our analysis, I think it is possible to check where it's counting from. So if we look at linear and then I think options, not options, statistics, no. That's not where it is. Okay. Okay. So I'm not seeing the option here, but I believe that this goes from the lowest to the highest. So it may not really make sense. You know, that's how research goes. Your expectation would be that the mental health score would be higher as you go from one category to the other, given how we recorded our data. So we recorded our data to say that 4 means someone who has worked 80 hours or more. So your expectation and my expectation would be that this person would have, anyone in this group would have higher mental health score, therefore poorer mental health than someone in this category. However, that's not what the output is telling us. Someone sound Jerry?
Yes, I think the output is making sense, because if you look at the mental health score, the higher the mental health score goes, it would mean that the person is more healthy mentally, right? So looking at it,
means the person is less healthy.
Higher the mental health score goes.
Yes.
So we are saying that the mental health score is actually measuring in the negative. So the higher it goes, it means the person is not healthy.
Yes.
Right?
Yes.
So that's the issue, because looking at it this way, thinking at the back of my head that probably if you have a set of questions asking on mental health score, and the person has to pick on a scale of 1 to 5 for 30 questions, and the person picks 5, 5, 5, 5, 5 all through, that would be a higher mental score than somebody who picks 3, 3, 3, 3, 3 all through. So looking at it, that if you walk lower, they may say, yes, one of the questions, they have more time to take recreational activities. On that scale is 5 and like that. But somebody who is working more hours, in this case, as the number of hours increase and as we go from the lower levels of 40 and below to 40 to 60 and all increases, that person's mental health score would reduce. That is if it was being measured on a scale, right? But now you said that's not how the question is asked.
No, that's not. So higher, for most mental health questionnaires, a higher value is worse, means worse mental health. So
that means we should have recorded 40, we should have recorded 80 and above as 1.
You would still go, if
we change those categories, yeah.
You would still interpret it in the same way. It's just that you would now have to remember that you started recoding it from the top. So you would have to put this negative sign in your mind as you are interpreting it, rather than having it here on the coefficient. So if you see something like this, results that does not make sense, especially when you are doing regression, it may mean that there are other variables you need to consider that can predict some of this outcome. It might be also because this is a significant predictor, as you have categorized it. It might be, but then if you look at the R square is very low, so that tells you there are other factors you have not considered, and it's possible when you introduce those factors, you would begin to see something that you actually expect to see. So this is not taking, is not telling the whole story. Okay. We have taken, we have about 40 minutes left to go. So is this particular example clear? Okay. So in order to also do, if you want to see this a bit more clearly, if you want to see this thing that we just did now, you want to see it a bit more clearly, like, right? You are just asking me this hours cut. Where is the category 1? Where is category 2? Where is category 3? Where is category 4? And I told you everything is embedded here. But if you want to split everything out, bring it all out so that you can see each one of them as individual variables, then you would create what is called an indicator or a dummy variable, which means each individual category of your categorical variable becomes a binary variable of its own. So it means that as you are, the category that you recorded as 1 would be a binary variable. The question would now be, is this participant in category 1 or not? If yes, the value will be 1. If no, the value will be 2. And we'll do that for category 2, category 3, and category 4. Does that make sense at all?
Yeah.
So I'm looking at this. I'm trying to determine if this comes from the same data set. Okay, yeah. So we are going to, no, we have done this. Okay. So we can create the dummy variables by doing it manually and making all of these a binary variable, but there's a function within SPSS that lets us to do that. So when we come to transform, and then we go to create dummy variables, we would then want to choose the variable that we want dummy variables for. So this is hours cat. That's the hours category variable. So the root value, the root name, basically is asking you what is the name, what name are you giving to the children of the main variable. That's the dummy variables. So we come to so we can say, usually when you create a variable from another variable, they're referred to as children. So if you had noticed from this previous table, you would see that they named it child cat, child category 1, 2, 3, 4. Anyways, then we go ahead, and I'm looking for where to create so the value order is ascending. If we say value order is ascending, it means that the child category 1 would be this one, and then category 2 would be this, and category 3 would be this, and category 4 would be this. If you put it as descending, then it comes this way. So we're going to leave it as ascending. Then it's been a while since I did this. So I'm just going to click OK and see what happens. Okay, so let's go back to our variable view. So nothing has happened. Okay, let's go back. Create dummy variables. Okay, and say open. Okay, so it's that was the option that I needed to create. The option I needed to select. This option that says create dummies for all variables. So it's not saying all variables in your data set. It's saying all variables that are embedded within this hours cat. And what are they? This 1, 2, 3, and 4. You know, we said that we have changed the categories into each category into a binary variable. So when you select this and you tell it what you want the root name to be, then it does that, and then it has just done the magic and recoded this variable into what's it called? Multiple variables, multiple dummy variables. So, sorry, you now bring, if you bring the, if you now want to bring these variables into an analysis, you come to analyze, you come to regression, you come to linear, and then you remove the hours category variable, and then you select these variables as it is going in ascending order. let's go here. Put them in here, and then you click on OK. So now, Debbie, go ahead.
Thank you. I'm still confused about dummy variables and why they're necessary. If it is that you are able to select or to recode or transform your variable into 4 categories, what is the additional benefit of dummy variables? I'm really not sure I understand what dummy variables are. I've never understood it, and I'm still not clear.
Yeah. So if we look at it, if we look at the, let me go back here. If we look at these categories, we have categories 1 to 4. You understand these, right? Just stay unmuted so that I can get feedback from you.
Yes, yes, I understand.
Yeah. Yes. So I guess the dummy variable would be able to tell us exactly at what range we have a significant prediction of the outcome variable. So if you just look at the previous example, where is it? Where's our previous example before we recoded? Okay, so if we look at this previous example, you can see that we're just looking at this recoded variable that has now become, we're testing for linear trend all within the variable, but we don't know exactly where the significant interaction is occurring. And we don't know if it is the same, whether you are moving from 1 to 2 or 2 to 3 or 3 to 4. So separating them into dummy variables now gives you an additional edge. For example, if you notice, if you do a histogram, for example, and you notice that there's a bimodal age presentation for a particular disease condition, and you now want to see if these age brackets, the 2 age brackets, maybe the young and the old, let's say under 5s and over 65s, whether this actually means anything. If you break this down into that kind of category, those kind of categories, and run the model, then it will be able to tell you whether or not these are good predictors of whatever outcome you are trying to determine. Does that make sense, or have I confused you further?
All right, let me see if I can clarify it in my mind. So what I'm looking at here now on your screen with the coefficients and our category 1, 2, and 4, those are not the dummy variables.
Those are the dummy variables.
Those are the dummy variables. Okay.
Yes.
All right. So if you had entered in the regression, switching over to the other side of the screen where you have these ranges, and for new value, enter 1, enter 2, so on. So if you had put those ranges into the regression model, would you get the same output as what you get from using these dummy variables here, or no?
Yes, if you enter these ranges as individual variables, if you decide not to categorize this as a, if you decide not to split this into a dummy variables that bear similar name with the parent variable, regardless of how you slice it, as long as you are having these range of values, you would still have this same
output,
this same result. It will just show you different names.
I see.
Depending on how you have named the variables.
Okay, I understand it now. Thank you very much.
You're welcome. I think I must have done something when I gave the instructions to SPSS to really exclude the variable. So as you can see, for this particular one, let me go back to analyze regression, linear regression. If you notice here, we have 4 different variables, right? So this is, I don't want to, let me just, for simplicity's sake, I would, this is a multiple linear regression because you have multiple independent variables. Now, the selection method that we have used, if you look at this, there are several different selection methods. I just left it on enter, and I've been leaving it on enter all this while because it doesn't matter what selection method you use when you are doing a simple regression. And for a multiple regression, that is when this becomes important. So I'll just try to explain what these things mean. So for enter, it just means that we have dropped everything into the model. SPSS has dropped everything into the model to see which one really works to be able to predict what the mental health score would be. So when you do a stepwise selection, or let's say forward selection, which is easier, this means that you first start with one, SPSS would pick the first variable, and then the next variable, and then the next variable, and so on and so forth until you have all the variables. So it will keep on doing this until it comes up with a model that it is happy with in terms of the R squared. So when it has a model that has a good R square or the best R squared with the least number of variables, it will stop there. Backward selection is the reverse. It will throw everything into the model and start removing one by one. This all happened in the back end, so we did not see it happening. But I'm telling you what's happening in the back end. So backward selection, SPSS has entered all the explainer variables into the model, and then it keeps on removing variables one by one until it gets the model with the best fit. Stepwise selection is a bit of both. So it will go forwards. It will do forward selection and continue going. But if it adds a model, if it reaches a point where it has added another variable and then the model is getting worse, it will remove that variable and then select another one and continue adding. So that's kind of what it entails. I don't know what remove is. So basically that's what it has done. It has checked to see which one is which of these variables are. Yes, Jerry.
So is that why we are seeing the third category being excluded, or is that why we can only see 3 categories? Why did it exclude? I don't know. I'm seeing hours cat equals 3. Yeah, it excluded 3.
It has excluded it because of what I've just explained in terms of how it works. Like I said, for enter, it drops everything inside, and then once it sees that there is a particular variable that's not good for the model, it just excludes it. But it doesn't.
So can we say that
all at once? Not compared to.
Can we say, okay, yeah, sorry, I'm having a bit of network lag, so it may seem I'm interfering. Would it mean that maybe there is no value under category 3? Because I see here we selected hours cat, but I think we did the dummy variables for child something, if I'm not mistaken.
Yes. sorry, analyze, is it linear? Yes, it has. This is how our dummy variables were renamed, and that's the reason why it's giving you this our stat something.
Okay.
I wanted to rename it as child, but I probably did not select the proper option. So it's
Or probably
renamed.
we were supposed to rename children, number of children, instead of hours cats. We're actually supposed to create dummy variables for number of children. I think we discussed that in the other class. I'm thinking it's excluding that variable because maybe there is no value.
Yeah.
Because I see everything is 0.
Okay, that means there's a bit of a disagreement between the what's it called? What's this name? The lab slides and the lecture slides. But regardless, you can do this for the number of children as well. You said that's what you discussed in class. You looked at
when we're talking
how
about
the number of children affects.
Yes, hours worked.
Okay.
So we discussed number of children and hours worked, and then we now went ahead to categorize into one variable where we had categories 0 to these children, this to that children, and then and then the slide had a dummy variable for children category where we have children 1, children 2, children 3, children 4, and then 1 and 0 for each of those recorded.
Yeah. So you do know how to do that. Okay, I can see that we have another 20 minutes, so we can go ahead and do that, and maybe even combine, apart from what the lecture slides are telling us to do, we can decide to combine, let's say, the number of hours worked and some other variable to see if that gives you anything. So you said you transformed the number of children. That's this number of children, right? Jerry?
Yes. So what we saw was number of children. So the analysis was talking about hours worked and number of children. Okay. And then it went ahead to say categorize number of children. So I remember we were saying that our C would be number of children. That's the number of hours worked when number of children is equal to 0 to give us our constant.
Yeah, that would be the
then
constant.
Then we went ahead, did it with just the raw figure, continuous variable, discrete variable or continuous, and then later we were asked to
do you know what the cutoffs were for number of children? We can really actually replicate it here.
Yeah, so I think the highest was 8 children. So we had to do maybe 2 children, 4 children, 6 children, and 8 children. So we had 4 categories. So we had 0 children first, then we had 1 to 2. 1 to 2, we had 3 to 4, 5 to 6, and 7 to 8. Something like
that. So I'm just trying to do histogram of the number of children to see okay, histogram. Yep, number of children. Okay. No, I'm not looking for categories anyways. So that would help us visualize the Okay, so there are people with 0, 1, 2, 3, 4, 5, 6,
And
6
6,
children.
yes.
Yeah. Okay, so we might want to see people who have 0 children. We might want to see people who have 1 to 2, then 3 to 4, then 5 and above. That's 4 categories.
Yes, 4 categories. Yeah. Sorry,
Okay.
I said it. Sorry.
Yeah. So let's recode into different variables number of children. Okay, so
so first of all, can we do this straight? First
sorry?
of all, can we do this? Can we do the dummy variable straight from number of children, or we have to first of all
We
create
can
one variable child cats?
we
And
can
get that
do it.
category?
We can do it. Where is
Okay.
it? I think we can do it straight, but it will give us. We're going to need more to do a bit more work because we'll end up still needing to create those cutoffs. Let me just do it the way we did it for this other one so that we take one at a time. Okay. Old and new values. So lowest through, so 0 to, it's actually 0 to
It's
0.
just 0 first.
Yeah, so it's just
category.
0. That is 1. Let's remove all this first. It's interesting how these things just stay there. So
0 was actually recorded 0, right?
So we go 0, 1, 2, 3, 4. So 2 to 3, 1 to 2 children.
Yes.
1 to 2 children is 1.
1.
Then 3 to 4 children is 2. Then
greater than 5.
Yep, greater than 5.
Or
5
greater
or more.
than 4. Greater than 4. So we have 4 categories.
Yeah, so 5 or more is 4.
No, that's supposed to be 3.
Sorry?
That's supposed to be 3.
Here we
Greater
have 3
than
to
5.
4. 3,
Yes.
oh, yeah, okay. I see what you mean. So let's remove this. 5 through highest. 3. So we click change and that's okay. So now we can do, we can combine this child's, where is it, analyze. So we can combine, let's remove all of this. The hours worked, like you did in your class,
yes,
with the number of children as a categorical
yes,
variable. And then you click OK. So that gives you this this equation. But like you said, it doesn't really tell you how this is changing. Although it's already telling us from here that just that variable child category, it might not be a significant predictor when you're combining it with this. But for the sake of argument, let's now use the dummy variable to look at the relationship between them. And you go to create dummy variables.
Sorry, why are we seeing both of them in the model? I thought one is supposed to be the predictor. It's still referencing mental health. So we are seeing both hours worked and CAT as a multiple regression. I think the hours worked was the dependent variable, and then child CAT was...
is that what you were trying to predict? You are trying to see whether people who had more children work more hours or less hours?
Yes, before now doing the dummy.
My assumption was that you were trying to see whether combined with the number of hours worked, the number of children predicts the mental health score. That's another question you can ask. So if you want to find out whether people with more children work less hours or more hours, you come to the same equation. You remove mental health score as the dependent variable and put the hours worked, and then leave this as it is.
Yes.
And then you click OK.
Beautiful. So from here, we now created dummy variables.
Yeah. So here it's again, it's saying that it's not a significant. There's no significant relationship between the number of children and the number of hours that you end up working. But let's break it down into those categories. That's where we use dummy variables. And sorry. So we move this. What time is it? We have 11 minutes. I'm just looking at the clock. So I can remove this. It will name it or not. In case, so we don't mistake it for the one that we created earlier. Create dummies for all variables. Click OK. So it has created four different variables from that variable called child CAT. Now, if we want to see exactly what linear trend exists when you compare this variable with the number of hours that people work, you go to regression, linear, and then you remove this and throw in the dummy variables. So then it's here, and then you say OK.
Voila.
So again, it has removed the first category. So, or rather, the second category, and then it gives you this what's it called? This table of coefficients. So here none of them is statistically significant, but for the sake of argument, you would say that this category is people who have no children. This category is people who have two. What's category 2? 3 or 4 children, right? So
no, category 2 is 1 to 2 children. No, sorry. Okay, yeah, 3 or 4
children. So it says it's saying that you find people who have 3 to 4 children working less hours than people in the previous group, and then here is saying that people who have, what's the number of children now? 5 or more children are working more hours than the people in the previous groups.
Are working less hours. Oh, there's no negative sign.
There's no negative sign. So that tells you that it's just an academic exercise for you to see how the tables come up, and and also to see how they can be interpreted. Maybe this is a point where I can, feedback to some of the other members of faculty to say that we should probably come up with data sets where these things show some particular types of relationships so that it is very intuitive to get. Debbie?
Thank you. A quick question. Why is it that the model excluded the dummy variable 1?
So it's basically the if you look at, let me go back to analyze. If you look at the type of multiple variable selection method we used the enter method, which basically throws everything on the wall and see what sticks. So what the SPSS does is that it goes into the back end to test different combinations of variables, and it comes with the model that uses the best model with the least amount of variables.
Okay.
Yes. So at any point in time, if we had used, let's say, forward selection, we'd probably come up with the same thing, because it's a very small, it's a relatively small number of variables.
Mm-hmm.
Yes. Yeah. So that's what the SPSS did, and it did that for even the previous categories that we created, where we categorized the number of hours. So it still excluded the category number 3, because based on the different combination of variables, this combination of 3 variables in this model gave the best model fit with the least number of variables.
Got it. Thank you. Thank you.
Okay, that's, I think, all we have time for today. We always have the platform where you can just type on the Google Classroom and ask a question. If you want to set up maybe a meeting with one of the people, one of the tutors, you can do that based on their availability. I would just give some 5 minutes for anyone to make comments or ask questions, or if there are any takeaways from today's class.
So just asking that we have treated both this method you applied, where we used dummy variables. Let's assume they were not dummy variables, but we are adjusting for confounding. Is it confounded or
confounding? Okay.
Confounding is the same. Is basically the same. Same role.
Yes. So you would just interpret it as, let's say these are all different variables. The way you would interpret it is that while you are keeping all the other variables constant, this is the extent to which this particular variable affects the outcome variable. So if everything else remains the same, let's say this is height, this is weight, and this is number of children. So this number of children, if you multiply it with by the if you multiply minus 3.102 by the number of children, it would give you the number of hours that the resident worked in that week, keeping other variables constant.
Okay.
Yeah, and as you can see now, here is where you still also have the standardized coefficients that I talked about, where I said these would tell you the extent to which this actually contributes to the overall model. So the R square is the overall predictability of the model itself, and then these standardized coefficients, you interpret them similar to R2, just that you interpret them as the predictability of that particular variable, of that particular independent variable. Is it predictability? I'm using the wrong word, right? Predictive power. So thank you, everyone. If there are no further questions, I will ask Ore to end the meeting here, and see you 2 weeks from now.